Okay, today in lecture we went through detailed solutions to the differential form of the momentum equation for a couple of particular cases. The important thing here is that we're talking about viscous flows. And so in each of these cases, viscosity and the friction associated with that plays an important role in the dynamics. On the left-hand side here we have a flow in a slot, a two-dimensional slot that is in the XZ plane. On the right-hand side, we're talking about flow in a pipe, and that pipe flow is directed in the x direction along the axis of the pipe, but is of course then in polar coordinates in the cross-section. Now in lecture I went through a lot of the assumptions that are required to get to these solutions. I would encourage you to go back and look at the notes to understand all of those. In essence, in both cases we assume steady flow and an infinite domain in the x direction. Additionally, in the two-dimensional slot on the left here, we also assume that things are uniform in the y direction. So we have the velocity varying only in z on the left-hand side, only in r on the right-hand side. With those assumptions, we can actually perform a double integration of the momentum equation. Essentially, the momentum equation reduces to the statement that the pressure gradient, minus 1 on rho dp dx, plus the viscous stress, specifically due to the change in velocity across our slot, have to be in balance. So the pressure term here, dp dx, and the viscous term balance to 0. Now we also have boundary conditions, v1 and v2, which allow for the boundaries to be moving. Integrating this equation gives us the solution that u of z is equal to minus 1 over 2, now I'm going to use the absolute viscosity, mu, times the pressure gradient, dp dx. And we have our z dependence, hz minus z squared. And then we have a second term that involves our boundaries, v2 minus v1 over h, all times z. There's an h in the denominator. This solution really divides into two components. We have a pressure-driven component, and we have a boundary-driven component. The two are added linearly to create the complete solution, which I sketched in lecture, and you can go ahead and plot that up. I want to move to the right-hand side now to talk about flow in the pipe. Now, when we're integrating in the r direction, we end up again with a quadratic, just like we do in z. There's one extra boundary condition that needs to be applied. Essentially here we assume that the outside boundaries of the pipe are motionless, and we require that the velocity not be infinite along the center line. After integrating this equation twice, we arrive at the radial variation of the axial velocity is the pipe radius squared minus position within the pipe squared divided by 4 times the absolute viscosity times minus dp dx. What that means, if I sketch this in the top panel, is that we have a velocity profile which is 0 on the two boundaries, is maximum along the center line, and is quadratic within it. Now I mentioned at the end of class today, or on Friday, that we can generalize this expression for pressure, and I'll do this at the beginning of class on Monday, but just as a quick preview, if the pipe is not horizontal, so non-horizontal pipe, then the pressure is replaced by pressure plus gravity, gamma z. That expression, which is related to the total head, appears in this right-hand side, and then we end up with the same expression. It's just that forcing can now be due to pressure and gravity in combination.